Okay, so welcome back to C467. So this is lecture number 5. We will focus on the foundation settlements. So last lecture we talked about the bearing capacity of your shallow foundations, which means we check out the soil, whether the soil strength has the capacity to handle the loading from the structure passing to the soil through the foundations. So if the loading from the structure is greater than the strength of the soils that can handle, then this is a no-go. So the factor safety is too low for you to do such design. So first thing, we need to make sure the soil is strong enough to handle the loading. Second thing, like we look at this lecture, is we need to make sure the settlement or the deformations induced by the loading, because whenever there's a change of effective stress, which is the change on the adding the loading to the soil will deform. And we need to make sure the soil is not deformed too much that you will create damage on the structure. Because like the whole thing is sink too much, then there's the structure will have a performance like effect. You can create cracks, or like the worst case, like excessive enough, like you will have structural damage. So this lecture, we talk about the learning objective is to understand, to know when to use which method. We introduce those modular space like method for immediate settlements. So we talk about what is immediate settlements. And also, we will talk about the tertiary consolidations, which part of it you have learned in 366 already. There's the primary consolidations, and there's also the secondary consolidations we will talk about in this class. And at the end of this class, you should be able to calculate settlements from secondary consolidations. You understand also not only uniform deformations, but also the differential settlements. We talk about that at the end of the class. So at the end of the day, you should be able to calculate the settlements from a given realistic geologic profile under structural load, just like your semester project. So this lecture will help you to finish your semester project as well. Okay, so let's talk about the big picture. So when you have foundations, shallow foundations, and real likely you are forming on the soils that come with like a different layers. So you could have a clay layers, you could have sand layers, and maybe under sand layers, and then you have another clay layers before hitting the bedrock. So, it could be anything. It could be sand and then sand, and the whole site is a sand site, or the whole site is a clay site. And these foundations come with like the geometry with a certain width and also a certain depth. So now the question is how deep is the influence? Because remember in the 366, in C366, we learn about this distribution of stress. And also we learn about the consolidations. So the consolidations, we have two parts. We have the compressibility and also we have the time rate. So the compressibility answer the questions of how much, and the time rate answer the questions of how fast. So the distribution of stress for which lectures that should able to help you to answer the questions is how deep is the influence zone. So we are passing the loading from the structures to the foundations, and you could imagine like right underneath the foundations, uh, whereas the stress concentrations is, but the load, the stress will kind of like a fade out through depth. So like, the deeper it goes, the less stress you will felt by the soils. So you kind of like have a zone that represent like, where the stress stop. Um, and the Tasagi have a guidelines, have a reference that this like a zone of influence is 4 times the width of the foundations. So if you're counting from the depth from the face of the foundations, so what you need to take care of is like a 4B plus D. So you want to ensure that like the stress that you have uh, that you want to look at the zone of influence like on the loading passing to the soils. You want to take care at least that zone right there, D plus 4B. And when the loading is put on the ground, then um, you will start to deform the ground, so you're causing the settlements. And what happened is actually like within the zone of influence, each soil layers, the soils will be deforming. So you have deformations from the first clay layers, and then you have the deformations of the sand layers, and also you have the deformations on this another layers that underneath that. So you want to find out all the settlements based on each layers on the soil type, and the soil types matters. So in our world, we have the clay layers, or clay soils, and also we have our sand soils. For the clay soils, remember in 366, we also start talk about this. The total settlements, you have three components. Yes, the immediate settlements, and also it has the primary consolidations, and also it has the secondary consolidations. And compare with the clay, the sand layers, for the sand soils, the most significant source of deformations is come from the immediate settlements. So for primary and secondary consolidations, sand, you will have the consolidations too. Remember in our CE 368, when we do the direct shear test in the lab, when we testing our sand soils, we put on the dead weight on the direct shear machines, and on the vertical alignment, you will see the vertical dial gauge, you will see the deformations of sand. So it happens, but if you remember that too, the deformations is tiny. So for sand, only for sand, not for clay, those consolidations, like deformations, is relatively insignificant when you compare with the immediate settlements. And in fact, when we once we place the dead load from on the sand samples on the direct shear machines, and actually like the settlements or the deformations over there is contributes from the immediate settlements. In overall, in general, sand we have a much less total settlements compared with clay. But the immediate settlements is something like we need to take care of for our foundation design, especially for sand. If you have a very complicated, like a very like an important structure, like for example, maybe you have a nuclear plant, um, that is so important that you need to make sure that you will last for 1,000 years. So you also need to take care of the secondary consolidations, even though you're on an entirely like a sand site, because every little bit count. It also depends on the importance of the structure. So those are immediate settlements, and also like when we learned 366. So this part, the primary consolidations, pretty much we take care of this in 366. And also like go back to lecture one, remember or homework one, we emphasize on those string and unstring conditions. And in order to do settlements like analysis, you need to well understand what type of conditions is it? Is it drain or undrain? because that would be affect the parameters for you to use. So even the same design problems, the same site, but if you have different like a drinking conditions, drain or undrained, you will have different answer, coming from different like parameters to be used. So we need to understand like overall, when to use drain and when to use undrained. And in general, we learned this in 366, right? Uh, for for the clay consolidations, we can solve this using the Tsagi consolidation method. Okay, so from those like consolidations like for clay, those are in drain conditions because those consolidations you would take months or years for clays to sites to have the pore pressure, the pore water to escape from the clay layers. So that's why like you will long that you allows you to have enough time for the water to escape the clay. So that's why it's a drain conditions versus the immediate settlements for clay. This is undrained conditions, so you'd be very careful when it's drained and when it's undrained, because the immediate settlements means like right after or within the construction times. So we talk about days, not months or years. We talk about days or hours. At that times, even if you have a clay site, there's like no time, not enough time for the pour water to escape uh, the very like very 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 like a less permeable clay. So that's why you would take a you don't have enough time for the water to go out the clay. So that's why it's undrained conditions. But for sand, it's the other story. For sand, for immediate settlements, um, because like a sand is very permeable, so the water can pass through the sand easily. So that's why like within the construction time, very likely you have a drain conditions, unless you have some very special design scenario, for example, earthquake, because earthquake loading will happens like within minutes, uh, at most maybe 2 minutes. So within that like a short period of time, even though you have a very permeable layers like sand, still don't have enough time for the water to escape the pore volumes, escape the soil layers, the sand layers. So for seismic design for sand, you have undrained conditions, so be very careful. But this is not an earthquake design class, so that's why like for sand for our applications, immediate settlements, it's safe to say this is drain conditions. So for both immediate settlements, um, we can use the method of we talk about more next, the method of the modulus based design. So modulus method. So we talk about more in details in the next starting next slides. So what are the what being available is for just an overview on what type of method we talk about. So those modules based method. So first we will talk about the simple elastic solutions. We talk about the generalized elastic method. So we also talk about the main and Poulos 1999 method. We'll talk about the most popular one, the Schmeckman method. So we talk about those methods such that at the end of this lecture, you should able to handle the design for the immediate settlements for both sand and clay. And we will also talk about the secondary consolidations. So hopefully, like at the end of this lecture, you were able to do a settlement design to complete like a suite of the settlement design. Because in 366 we just talk about the primary consolidations of clay. But the full picture is like, you also need to look at the immediate settlements and also the secondary consolidation settlements. So we talk about all those, and after each components, you add them up, then you have the total settlements for one layers. So for each soil layers, you need to take care of the both all the three different components, immediate, primary, and secondary. So you can find out the total settlements for the first layers, and then also you can find out the total settlement for the second layers, as well as the total settlement for the third layer. So after you find out the settlement for each layers, then you can find out the kind of like the total of the total settlements for all layers. So the total settlements for the whole site is the summations of all the layers, the settlements, the total settlements of the layers within the inference zones. So that will be equals to the summations of all these layers. And the big picture is your design. You need to make sure there's like a total settlements of the site is less than the allowable structural settlements. The structural allowable settlements for the structure. So you need to make sure, like the structure can handle uh, the deformations. This is the allowable structural deformations. If your settlement is too large, which means then you will create structural damage. Um, the slab could crack, or like the columns and the shear wall or the any like slab attachments get detached, so that will create performance like problems, and you may like very dangerous okay, so first let's look at our very first simple elastic solutions. So the first modular space method, which is the simple elastic solutions, and it come out from Polos and David's 1974 paper. So first, it considers two scenarios when we have flexible circular footings. So the limitations of this method is it only work for circular footings. And also the other one is the perfectly rigid. So there's a typo here. So this should be rigid. So one like being perfectly flexible. So uh, when you're low on the ground, so that's why like the footing is kind of like deformed in a way like like a smiling face. Versus the rigid one, there's no bending on the footings, so the whole thing like deform uniformly. So that's just the perfectly rigid like a circular footings. And for each of them, you have your formula. So the deformations for that is the Q's times B for 1 minus the Poisson ratio square divided by the modulus. So that's why this called to be the modulus based method, is because it depends on the soil modulus. So kind of like a small string behavior. because the soil behavior is kind of like a stress strain curve. It highly depends on the deformations. So the response of our soils, it depends on how much deformations to talk about. So this is a very small string of deformations because the elastic modulus, it happens at the elastic range of soil, which is a very tiny deformations into 10 to negative 4 millimeters type of like a deformations where you have the elastic behavior. So the formula here is talk about the elastic solutions. So this is based on theoretical derivations. So uh, the whole thing is very theoretical based. The formulas is not empirical, but based on elastic theory. And the Q there is the applied bearing stress. So pretty much is the loading from the structure. B there's the footing diameters. So this method only works for circular footings. And you have the Poisson ratios. And also you have the Young modulus of the soil. So this is the soil properties. Talk about the soils. And the formula for the rigid response is the deformations equals to Q, again the stress times pi over 4 times the diameters, and then 1 minus the Poisson ratios over the Young modulus. And in order for this theoretical base framework to work, there's a couple of assumptions. First, you only work for circular footings, and the footings on the ground surface. So you only um, valid for the footings that uh, is right exactly on the ground. There's no excavations. Unlike many cases, you may need to the footings will go into certain depth in the soils, but this simple elastic solutions cannot handle that. So this is theoretical based method is great, but you need to understand the shortcomings. One of the major shortcomings is you cannot handles when there's excavations, the face of the footing go into the ground. And there's assumptions is also the response of the foundations is either perfectly flexible or perfectly rigid. So if you're perfectly flexible, you will use the formula on the left, and if it is rigid, then you use the formula on the right. And also, we assume the soils over there is isotropical soils, which means you only have one soil layers, and give you a single modulus and also Poisson ratios values. Because remember, previous slide we talk about the our like a ground could be you have different soil layers, sand, clay, and sand, or or any combinations that you may have. But here you assume that the whole soil layers is just one kind. So you just and then you just have one soil property parameters, more just the Poisson ratios to describe the soil properties. So those are the assumptions. Um, so I put some tables on the right hand side for us to able to estimate the soil properties to be used, and there's questions to ask. So should the both the modulus and also the Poisson ratios, should that be drained or undrained? So that's why in the previous slides we talk about that. Is very important for each scenario. Even though when we talk about immediate settlements, now we just talk immediate settlements, should they be drained or undrained? So if you for typically for clay, we will design for undrained behavior. But if you use like a drain parameters to do your clay calculations for immediate settlements, that's wrong. Be very careful because like like a simple parameters like for the song ratios, they have both like a drain or undrained like cases. So for this case, like for clay, we only put on the undrained because clay is under the immediate settlements, immediate like conditions. The drain gauge is undrained. For sand, it's drained. And those are the numbers over there for you to choose whether you have like a dense or loose sand. And for this class, we only deal with like a saturated conditions. So pretty much like, for clay is almost like always zero point 0.5, at least for this class. For sand, it will be a little bit depends on the density. So that is the Poisson ratios, and also like for the Young modulus, then you can use this chart to try to estimate that. And the modulus here, since this is for clay, so this is undrained modulus. And you'll be equals to beta times the SU. And the beta value is on the y-axis. So when you have a clay, the first thing you look at is the plasticity index and also the over consolidations ratios. So remember this one, the OCR is equals to the maximum pass pressure divided by the current effective stress. So we talk about this in 3662. So if you need to like refresh your memories about OCR, overly consolidated ratios, then please go back to the previous lecture from a geotech class. So after you able to calculate the OCR and then you know the PI, the plasticity index of your clay, then you can estimate beta, and your modulus will be equals to the beta times the undrained shear strength. So this is undrained shear strength. So we talk about this in 3662, the strength of the soil. And in fact, you see there's quite a bit of uncertainty. For example, you have PI of soils that is less than 30. Then like you have a huge range in terms of different like OCR. So I believe this should be greater. This is from a textbook. So those graphs are from a textbook. I believe there's maybe a typo on this figures. So based on the plasticity index and also OCRs, the range of uncertainty difference. So the higher the OCR, the greater the PI values, the likely the smaller the range. Otherwise, if you have normally consolidated, which means the OCR equal 1, and if you have a very small PI, then the uncertainty for the Young modulus could be huge because this beta, the range of this beta value will be huge. If you design, if you want to be conservative, you may want to pick this point, or like if you want to get a ballpark of things, like you may want to take the average. So those final comments about this like a simple elastic solutions, is the positive thing about this, the good thing about this is first, this is a theoretical base method, which means the formulas over there is can be backed up by physics. It's not like empirical base, but you need to understand that like the nature of soil is a lot of uncertainty, like the modulus values that you're seeing here. So the settlements itself is very hard things to estimate. So that's why down to the analysis, down to the design, you need to emissions. There's a huge uncertainty coming with it, and as engineers, you need to make the best judgments, engineering judgments to to choose the parameters to be used and then to come up with a reasonable settlements. So that's the challenging part of geotechnical engineers. Okay, so the next method that we want to discuss is the generalized elastic method, come from the original paper, James Law 1956. So from the previous method, we see all the limitations, like you only work for circular footings. You also only work at the ground surface, and you'd also have limitations of you only can take care of one kind of soils that give you a single modulus and also Poisson ratios right there. So this method is, in a sense that maybe a little bit better because it account for some flexibility. Like you account for the footing shapes, you account for the footing depth. You also you can take finite thickness of the layers. So what we try to achieve here, or what one of the expectations I have for the class is. After this lecture, you will know the shortcomings of each methods. So for your design, you know which one to use. Some method may be better for some scenarios, some method may be better for others. So you will be your jobs, engineers' jobs in the future, is to come up with the most appropriate design procedure. Sometimes like a geotech design is like a piece of art given the same site, but if you given to different engineers, they may have different answer. None of them are wrong just because maybe they have different approach. They have their own ways to interpret the site and also the understanding of engineerings, and then using different approach and method and come up with a different answer. So as engineers, you need to understand all the limitations behind for each method, such that you will be come out with the most realistic solutions. So this method is a little bit different, and the formulas is the I naught times I1 times Q times B, and then divided by the modulus. So the Q again, the Q is the average bearing stress of the soil, and the B is the footing width. So this is the B right there, and the E will be the average soil modulus. And I naught is the yes, I naught and I1, those are correction factors. Because remember, like the previous method, even though this is that is like a theoretical base, so this one is empirical base. So based on like a research data, based on field data, and they come up with an empirical approach to form those equations. Versus like the previous ones is purely like a theoretical. So the correction factors, you have I naught, we try to correct for the depth, because and the I1 is try to correct for the footing depth, sorry, footing shape, and the thickness of compressible soil layers. So first, the depth factors that you try to correct for is this one. So if you know the foundation depth here, divided by the width of the foundations, you can find out the I naught. And the other one, the I1, is this factors over there. First, based on the thickness of compressible soil layers. So from the face of the uh, foundations to until like all the way to the bedrock level. So what our very stiff, highly overly consolidated soils. So maybe you can assume like you go to the bedrock. So the depth over there, or like for the soils that being compressible. Some soil is so hard, or you have a dense sand, then it's not compressible. If you have a highly overly consolidated soil, it behaves like rock, then that is not compressible too. So based on the compressible layer thickness derived by the width of the foundations, so that will be your x-axis, and then you need to choose one of the contour lines over there, which is by the R over B ratios, then you can pick one. So if you have a ratios of 2, if you have a ratio of 5, if you have a square or circular, it's a ratio of 1. If you have a ratio of 10, then you will choose those curves. If it's something in between, then you need to interpret. For example, if you have uh, a 2.5, then you will kind of like choose the curve that you will kind of like draw a line that is like exactly between 2 and 5. Sorry, not 2.5. So that would be that's 3.5. So 3.5, then will be between 2 and 5. Then you will pick the point over there at the given x-axis, x values that you know. So with that, then you can come out with the factor of like I1, the factor of I1. So this method is again try to account for the flexibility. So now you can correct for the shape, correct for the footing depth, and also the finite thickness of the layer. But one thing you still haven't be fully adjust is the modulus values. You need to either measure it in the lab or use very uh, rough estimations like a chart like this. Why this modulus values always given us a hard time is because the modulus values for soils is not like a simple single number representing the whole soil layers. Uh, Pretty much the modulus values is depends on the stress state of the soil, which means like for something like the deeper you go, this value will change with the depth. So if you just try to use come up with one values to represent the whole layer, that is not enough. Enough like you come up with like a huge uncertainty that kind of like represent by this graph. So if at this point if you want to be a very good like a designer or very good like engineers on foundation design, you need to truly understand like a soil mechanics. How the stress strain response of the soils, why the modulus values that depends on the deformations. Are you designed for a small string problem or large string problems? What kind of deformation are you expecting for a design? So those will go into the next level of the details of geotechnical engineering, like a design. So the third method we talk about is Main and Pollock's 1999 method. So we talk about the previous two method, which is simple, and the major shortcoming is the modulus. So all this modulus based evaluations or a procedure to try to find the immediate settlements. Modulus is the key. And those two methods kind of is too simplified. They just use the one values, a constant, to describe the modulus behavior of soil. So you need to understand that for soil, it is not a homogeneous material in terms of properties. Even though like the same layers, for example, if you have like a soil here, well, actually this Main and Polo's method, they try to capture the modulus values with a profile. So you see, they try to model this modulus even within the same soil here. They try to model the modulus with the value that's increasing with the depth, which is true because the deeper you go, underneath our ground, the stiffer and the stronger the soil is. So they try to make some adjustments over there. So how they do it? Uh, the framework, they try to estimate the immediate settlements with these equations with three correction factors. So this IG, IF, and IE. So, and also you observe that actually the equations is kind of similar to the very beginning one when we talk about the simple equations. That is a theoretical base. So the very first one we talk about the elastic, simple elastic solutions. So those are theoretical based. So the framework is kind of like in the right directions. But later on, like the engineers, the academician, they try to advance the method, uh, based on improving it, like making on the weakest point, which is the modulus. So let's see, like how they do it here. But the major framework is there. So now we have three correction factors times the middle part, and then 1 minus the square of the Poisson ratio. So the E naught over there is the soil modulus directly below the footing. So that's why E naught is here. And they started the depth here at the face of the bottom of the footing. So this point is your E naught. The BE is the equivalence circular footings. So this method only work for us, not only work for circular footing, but what you do is when you have a square or rectangular footing, you will kind of like transform it into a circular footing with this parameters. This is the equivalence. Circular footing equals to the square root of 4 times base times length divided by pi. And all these three are the correction factors. So the IG is for the finite thickness, and soil modulus. And the IF is for the footing rigidity. I sub E is the footing embankment depth. And this is the Poisson ratios that we know. And the I sub F and I sub E equations are there. So realize on this that I sub F, that's this parameters E sub F here. So E sub F is the modulus of the concrete. So this is the modulus of the concrete, or your foundation material. And that's also another very important parameters is this K. So this E naught and K over there is trying to capture the behavior of the modulus. So now it's not a single number. They try to model the increase of the modulus with depth with this E naught and the K. So the K is sort of the slope of this line of the change of the modulus, and they would use this. The modulus is proportional to the enduring shear strength. So, oftentimes engineers will find out the undrained shear strength profile, and then to convert that to the modulus profile. So next examples, we will see how to do that. So those are the parameters, and the T pretty much is the thickness of your foundations. B sub E, we talk about that. And the D sub F right there is the depth for your foundations. So this is the basic framework, and I sub F and I sub E. And I sub G, you need to use this like a chart to find out the I sub G. So you calculate beta, which is based on the E naught and K again. So the K will be very important, and as well as the E naught. So you calculate the beta, and then you know the C sub H over B. So C sub H is pretty much like the thickness of the compressible soils that you will be looking at, and then developed by normalize it by the width of the foundations, and then you got the ratios, and if you get values like kind of like in between those like contour lines, then you need to interpret them. So this is the basic framework, and the next slide we will try an example. So next, the Schmackman's method. So this method works very well for the sandy soil. So when you have sand profiles and then you want to do uh, immediate settlements assessments, the Schmackman method is a way to go versus the previous one, the Meade and Polos like the 1999 method. You work well for the clay soils. By the end of the day, which method is better, I think it highly depends on how well each method capturing the modulus values. So the previous method, work uses like a design to be compatible with undrained shear strength, which is like ideal parameters for clay. This one, we will use the displacement, the strange approach, which is good for our cohesiveness soil. And this method is designed with compatible with CPT results. So if you have a sand site, that you need to design for, or your project is on a sand site, and immediate settlements is very critical. So you at the back of mind, before you do any design or even before your geo explorations investigations program, since like this is a sand site and the immediate settlements is critical. So pretty much like you better have some CPT measurements. After you have your CPT measurements, you will work really well for this Schmeckman method. If you only have SPT data, you need to convert that to CPT in order to use this method. So you add one more layers of uncertainty or like conservatisms to bring in. So if you're smart at the beginning, or you have all this knowledge, so you will know what to do at the beginning. So this method, each use a lot on it depends a lot on this parameters. What is the strength influence factors. So which means the immediate settlements or the modulus values highly depends on the formations, because the strength, right? The strength pretty much is the deformations divided by the thickness. Anyways, and then you have this method, it has a key this chart. You can see the profile here. This string influence factors. It has two two parts, and then it is break down by one key parameters there, which is the I epsilon p, which is the stand for the peak string influence factors. This is the peak influence factor, and this is equals to 0.5 plus 0.1, the square root of the CPT tip cone resistance. So that's why CP is important, divided by the two stresses. And
the Q here is the bearing stress, which is your CPT measurements. And the sigma ZD is the vertical stress, depth D below the ground surface. And the sigma pi CP is the vertical stress at the depth of the peak influence, string influence. So here, like, you have like a two, like a, uh, lines right there, or two like parts over here. One is the, this is kind of like the square footings, because the R over B is, the length divided by width is equal to 1, so it depends on the geometry of your foundations. And your curve will start with 0.1, the line will start with 0.1, and this part will be depends on the depth below the bottom of the footings divided by the width of the foundations. That will be equals to 0.5. So that is the locations of the C sub F. So pretty much like the location of this point. So if you want to find a C sub F, it will be equals to 0.5 times your width of foundations, and then after you know this depth, then you can calculate your vertical stress at that point. So that will be the corresponding to the effective stress at the depth of influence factors, peak string influence factors, and this one is greater. So the other like dotted lines here is for the like rectangular, really long footings, and you have this point. You have a ratios of uh, of 1. So the location, the depth of the string peak string influence factors will be exactly equals to the width of the foundations. So that's how we calculate those parameters. And at the end of the day, what we need is try to establish this two line for your project. So it will be depends on the as you can see, it will highly depends on the width of your foundations. So you will want to draw those lines, uh, and then like find out this factors at any depth that you will need, and we talk about how to do that in the next slide on the procedure. So eventually, like after we figure out those parameters, it allows us to start to able to calculate the settlements and the immediate settlements for sand using the for sand layers. You are using the Schmeckman method. This equal to these equations. So the settlements equals C1 times C2 times C3, the CBT measurements minus the theoretical stress at the depth that you're looking at, and sum up all the layers. So we talk about like how to find out this part on the layers later. So which equals to influence factors that you get from this graph times the thickness of the layers, and then divide by the modulus. Again, this is a modulus based like method, so the modulus is very important. So this terms is the immediate settlements for sand, and then you have some correction factors like before. So you have depth factors, you have a long-term settlements like an issue. So there's like a creep correction factors. You have a shape correction factors, and also so those are correction factors. One more times, and come up with this the string influence factors, which you interpret from the from the figure here. So this figure, so this string influence factors. So this is kind of like the factors is like a depth dependence. So this is like the depth normalized by the width of the foundations. So the particular location looking at will be at the midpoint of the layers. So this method you will require to divide your soil profile in different layers. We will do examples to show you how to do that. So when you get to that point, hopefully it will make more sense to you. But like these numbers, you have many of these numbers because you have like many different layers. And we will look at the midpoint. And the H will be the thickness of the soil layers that you're looking at. The E sub S is the equivalence modulus of soil layers. And the time, uh, the time is show up in the C1, 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 C2, and C3. So what are the C1, C2, and C3? So the C1 is the correction factors using these formulas. And the C2 will be this formula. So C2 is trying to take account of the time effect, so which is quite powerful. So it's the time greater than 0.1. And C3 will be the maximum between the three. So seeing this method can handle like the creep problems. So actually the settlements at the end that you try to interpret at the end of the day is not just immediate settlements. So it is also include like a primary and secondary consolidations. So this Schrackman method is quite powerful. So it can help you to interpret the overall settlements for sand, only work for sand. So C3 is 1 minus 1.03 minus 0.C3 times this, and then all 7.373. So there's a cap over there. The shape factors. So like it now only depends on the length and the width of the foundations, and it's capped at 0.73. And on the C2, the T over here is represent the time. So this is represent the time since applications of loading. So if you want to look at the settlements, maybe 5 years from applying the loading, then the time here will be 5 years. If you just look at maybe a week after the constructions, then your time here will be 1 week. And then B and L's the width and the length of the footings. So that is the basic framework for the Schmeckman method. And to use this Schmeckman method, that's like a certain procedure. First, you will perform appropriate in situ tests to define the subsurface conditions. So this method will be highly prefer the CPT. If you don't have the CPT data, you need to find ways to convert your data equivalence to CPT measurements, which is like you don't want those correlations on correlations. This is not good engineering. And then next, you will define the E sub S as a functions of the alpha using the CPT data. So the CPT, the CPT measure the tip cone resistance and also the sieve frictions. Those two measurements will help you to correlate many different parameters your homework too. You work for friction angles, you work for the strength of the soils, you work for the unit weight, and in fact, those correlations. There's also correlations try to relate the E sub s, the modulus values, with CPT data. So this allow us to do that. And next, you will consider the soil from the base of the foundations to the depth inference below the base. And this depth like a range from 2B for square footing and 4B for continuous footings. And so pretty much like, you have your foundation, right? So now you need to decide how deep you want to look into. So if this is a square, then you will this will be equals to 2 times the width of the foundations. This is the width of the foundations. And if this is a continuous footing, so that will be equals to 4 times the width. Depends on the geometry of the foundations. Next, you will divide this zone here into layers, and you assign represent E sub s values for each layer. So again, like on the Schmackman method, there's a summation here. So the summations means adding up all the layers. So you need to look at each layers individually. Um, so each layers So on each layers, the required numbers of layers and thickness of each layers depends on the variations in E sub s versus the depth profiles. And for hand calculations, typically 5 to 10 layers are appropriate. So the safe side, maybe you can use like 6 or 7 layers. If the in-situ test that are available in electronic formats, so like such that if you like using a timesheet to obtain the data. You can like automate those with your time interval of your measurements. So like CPT, like you push your cone into the ground at like a certain time rate, so you get all your discrete like a data like lines or data rows, and maybe you can just use the weight, so which means you can know the thickness, right? Because the weight times the time that give you the travel distance, so that will be the thickness of each measurements. Then from there you can automate using programming or like a spreadsheet to automate the calculate settlements for each layer. So it's quite powerful. So what does it mean here now is like for example hand calculations. Then you need to subdivide. Just add a color. You need to subdivide like your soil profile into different layers, so on and so forth. And uh, each layers you need to compute all the parameters that you need. Like you need to have the CPT that you have measurements represent the layers, and then you need to find out the modulus that's represent each layers, and the influence factors, right? Influence string values that you also need to come up with too. So those are parameters you need to find out for each layers. This is the layer 1, layer 2, layer 3, layer 4, so on and so on. And then, well, up to the boundaries that you define at the beginning. But like how many sublayers that you need, like it depends on your on your modulus values, and also depends on how you measure them. If you have an automated spreadsheet, you can divide this into many layers. But if you're doing hand calculations, for example, homework or exams, I think 5 or 6 layer would be fine, um, just for education purpose. Okay, so next also you need to find those like a C1, C2, C3 parameters, and then like you at the end of the day, like you find all the informations, then you can use these equations to solve for the settlements for your sand site.
Okay, on a quick clarifications on this slide is the Q that we mentioned before. for the Schmeckman method, actually both of them are the bearing stress from foundations. Those are not the resistance from the CPT. So both of them are the bearing stress from the foundations. So just like we have calculated in the previous lecture, lecture number 4. And we will do example explain a little bit more about that. So the tip cone resistance, the CPT, are needed when we use it to estimate the modulus values. So the CPT are not used in the Schmeckman calculations here, but this value is correlate with CPT. So that's when we need to use the CPT. Okay, next, let's talk about the consolidations. So we remember like settlements, it come with 3 parts, right? It come from the immediate settlements, the primary consolidation settlements, and also the secondary consolidation settlements. So later of this lecture, we talk about the secondary consolidations, and we have already taken care of primary consolidations from the previous slides. But those are modulus-based analysis. So a quick recap on the primary consolidations. In fact, we talked about that already in your previous class in CE 366. So there's lecture 8 and lecture 9. We talk about the compressibility and also the time rate on the primary consolidations issue. So I highly recommend you to go back to revisit. We don't have time to repeat everything here for this class. And on top of that, we also need you to review like the stress distributions. So stress distributions pretty much is uh, tells you once you change the stress, very likely for this case we apply a loading from the foundations past the soil, and the loading that we load on the ground, it kind of like the clay with it kind of like a decrease with the depth. So at certain points, like there's no influence anymore on the change on the stress. So we want to find out how deep and how far that the influence zones that happens from the change of the stress. So now we are on the missions on design the foundations, and your textbooks pretty much like this is from Tosaki recommendations. He give you some guidelines on like how deep you should look at beyond like your foundations, and also how to divide into layers for the settlements. So there's 2 cases like from these tables. You have a square footings and also you have a continuous footings. Um, so what it does here is, for example, you have a square footings, right? So this is kind of like a square footings. And this is your soil, your ground, and then this is your foundations. And what is the recommendations here is you need to divide or the soil, the compressible soil underneath your foundations into 4 different layers. And the thickness of each layers is layer 1. You have thickness of B over 2, same as the second layer. So this is the first layer, this is second layer, and the third layer we have a depth of B, and then like the fourth layers we have a depth of B. Remember, we need to do this because so assume like the whole soil stratum there is homogeneous. So we try to simplify our problem here. Just look at like you have a consistent soils like throughout the from the ground to a depth of like a 3 B. So B is the width of the foundation, by the way. So it depends on the geometry of the foundation. So 3B, which is 3 times of the width of the foundations deep to the ground, assume the soils properties there is homogeneous, which is not true, but for most case. But like this is the first step. We try to look at this problem, so that's why we simplify a lot of complex uh, factors of geometry there. But anyways, like we will divide this into 4 layers, and each layers, you calculate stress at the midpoint of the layers, and then you will do your settlement calculations because you know the vertical stress uh, at the midpoint, right? Just like exactly like 366, what we have done for our settlement analysis. And this is for primary consolidations only. So here, the slide, we deal with the primary consolidations. We'll talk about secondary consolidations later. So, you know the stress, and then like before you lay down the foundations, and also you know the stress after uh, you lay down the foundations with the additional amount of loading of each layer. So the final loading will be equals to the vertical loading, original loading, plus the change of the stress, right? Because your foundations give you the change of the stress. So now we know like the change of the stress before and after, then you can perform the settlement analysis. Why we need 4 layers again is because like if we just use 1 layer, then what happens is if you just use 1 layers, then you will just look at the stress at the midpoint of the whole layers. So if you just use 1 layer, so this is 3B, right? You will just look at the stress at 1 layer at the midpoint, and you look at the immediate, the original stress, and also we look at the final stress. That well, so the final stress will be equals to the uh, original stress plus the change of the stress. So the problem here now is if we just use 1 layer, this like a change of stress may not be accurate because uh, we know that like once we put down the foundations, the stress that you have here and then fell by different depth will be different because again this stress will kind of like the clay. So the deeper you go, the less of this stress, like the soil will experience. So right underneath the foundations, you will have all the stress, right? But when you go deep enough, this stress is gone, and you have like the clay in the way. So we have different method we talk about in 366 using the DM values. DM 7.1 like a menu, and then like there's some like design chart to find out the factors like how the stress change with the depth. So that's why we need to divide this like into different layers, such that we have a better capture of the change of the stress from the foundations. And we want to balance like between like too many layers with like just enough layers. And these are the recommendations from Tosagi are based on the square footings. So that's the approach that we try to find the settlements for primary consolidations. So from each layers, we will do like a settlement analysis. So each layers we will know the settlements. So we know the settlements of each layers. Uh, let's call this sigma D. So sigma D 1, 2, 3, and 4. So each layers, like we will know the amount of deformations. And the final settlements, the total, will be the summations of all the settlements of each layers. So the more sublayers that you have, the more accurate. So that's the suggestions for the square footings. And Tosaki also have the suggestions for the continuous footings. So when you're now like when your foundations is long, in a way like something like that. Then you will divide your layers. Where we have 4 layers again, but you will look at like a deeper, greater depth. Uh, to this time it's like B over there's like a 5B right over there, so 5 times the width for the foundations. So well, if I just try to be consistent with my previous drawing, so so this will be the width of the foundations, but it's continuous in the other way. So this is a very long, like continuous, like footings. Um, and you will look at like a greater depth to 5 times the width for the foundations. And you have like a BB, 2B, and 2B. So you have the first layer with a depth of the width, and then you have two more layers that you have width of two times the depth of 2 times the width. And then again, each layer you do your settlements analysis. Then finally, you will have your total settlements. And this is just for the primary consolidations. And the total settlements, like we have 3 parts. This is just one of the 3. So I want to highlight on some like minor points here. Also discussing the textbook. So those are just recommendations. So this is just a recommendation for you to get started. And you need to adjust the number of numbers and the thickness of the layers account for the change of the soil properties. So remember at the beginning, I told you I assumed the whole layers here is homogeneous, but if you have different layers of a soil type, you pretty much like if you have sand and clay layer, or like a silt or sand layers, or like dense sand versus loose sand layers, each layers you need to like do its own settlement analysis. So you have a very highly like differentiates or highly like variable soil profiles, which likely you will need to do many layers of analysis. So that's first thing. And also for rectangular footings, like the book or like Kazaki also recommends use layer thickness between those given of for square um, and continuous footings. So which means if you have a rectangular footings, you want to use something like in between. For somewhat thicker layers, um, so it also the third point over there mentions like you may want to use like a thicker layers if the groundwater table is very shallow. So if you have groundwater that is near the ground surface or like close to it or right at the ground surface. So you want to use like a thicker layer. So you don't want to just stop at 3Bs or 5Bs. You want to go a little bit deeper with thicker layers. So for quick but less precise analysis, use a single layer with a thickness of about 3B. So here's just a recommendations. If you're doing your analysis like on site, you don't have like the time or the computer or like whatever like a paper to work on, or you need to come up with something quick. Uh, uh, you can get the ballpark estimations by using one layer. With the depth up to 3 times the width of the foundations. But keep that in mind, those are just like a ballpark estimations. Once you go back to the office, you should do a more details and analysis. Okay, next, let's talk about differential settlements before we get into the secondary consolidations. So what is differential settlements? So differential differential settlements happens when the ground, the soils is not settling uniformly. So if the whole building sink uniformly across like the slab or across the foundations, you may not create as much as problem when you have a defensive settlements. So you imagine like this could be um, some soft soils at certain spot, then like one spot like underneath the columns like this K here is shallow more than like the other columns. So you will create like structural problems on the slab or the connections between the structure. So is something like you want to avoid at all costs. But anyways, like what is defensive settlements? It's just the settlements between two footings or between like two footings is difference. Why this happens? Could be there's like variations on soil. You may have like a pocket of soft soils at certain locations, or maybe like you have layers of soft soils that are thicker at one place than the other place. So that's why like the geo explorations, the geotech investigations program is very important because you want to capture those like soft soil pockets as as much as possible, such that like you can help you to minimize or to prevent the defensive settlements problems. And sometimes the variations is not from the soil; it's because from the because of the structure. So if you have for I don't know like what special building it is, but like if you have a very concentrated the load that give you a high amount of loading at certain locations. For example, maybe you have a very heavy water tank. Somehow, like I don't know why the structures they design at a special like a corner. Then it could happens. And also like maybe because you have like a different construction tolerance within the structure. So when this happens, so this those are some picture examples of what happens when differential settlements happens. Again, if the whole building like a sink at a uniform rate across the whole slab, then like that may not be too much of problems. But if you have a soft pocket right there, then like the building could tilt. Uh, if the slab is rigid enough to hold on to the differential settlements. If not, then like you could create cracks on the structure. You may have very serious structural problems. So again, like if you have like some different soil conditions right there that like you didn't for the design process before the constructions, the engineers didn't like take care of this issue. When times go by, because like a settlement is depends on time. When time go by, so this will come back to damage the structure, then you may have a differential settlements. So some like a field picture, when we see like some residential building, if you see a crack that only happen at a corner, uh, it just only happen at a particular like shear wall or like outer wall, uh, then very likely it happens because of differential settlements. So either like we have a different soil profile at very soft soil pockets underneath that specific locations, or like you may have a very concentrated like a structural loading, a poor structural design that to let that to be happen. So the combinations of both. So that's uh, a topic that like we always need to pay attention to as a geotech engineers. So that's like some methods to find out the defensive settlements. So methods to find the differential settlements. So differential settlements is the delta D right there. First is to compute the total settlements at different locations. So the total settlements means both immediate primary consolidations and secondary consolidations. So we will consider the best and worst scenario. So now you know very likely you use this method because you know um, the soil profile is different. So based on different soil profile or different like structural loading combinations, you know, if the loading is not uniform, then like at different locations, you will be able to compute the settlements. For examples, like you know the soil properties here, which have a different like C sub C. For example, this is a primary consolidation issues. So you have like a different compression index right there. So you will perform a settlements analysis at these locations and also perform a settlements like a analysis at these locations, adjusting to both like a immediate, primary, and secondary consolidations, and and then to see like how differentiate from location to locations. Quite straightforward, like that way. The other like a quicker approach is to use the differential settlements and total settlement ratio. And pretty much this is like dictated by some of the guidelines or like a design code. Depends on what you're designing on. Some typical guidelines is the soil dependence. So you have the sandy soils and also coupled with the structure, right, versus you have a flexible, rigid structure, then you may have different like design values for you to calculate that. So if you have a lateral soil for sand, if it is flexible, then your differential settlement is more forgiving. And for something like you have a rigid settlements, so rigid structure and also compacted field, then your settlement ratios tolerance for the differential settlements will be much less. So you apply for both sand and clay soil. And this is a design chart that like put by research paper in 1963. So at different like a structure, whether you have a rigid structure or flexible structure, then you have different guidelines right there. And your guidelines or your design criteria may have a different ratio to start with. So this is based on like the performance you are designing for at the first place. So now the question is like, which reference to use, then you will depends on the project. So, or like very likely you need to discuss with the structural engineers, what are the tolerance the structure can take. So like, the structure size, they may have some code or reference to pass it to the geotech, and then like from there, then we can know about the differential settlements. So kind of like this is like a backwork analysis, or like to find out how much settlements from the soils that can take, knowing the design criteria from the structural side at the first place. So, but anyways, those are some like some reference numbers and put together like some K history past. So you see all these data points is some K history where what are the maximum differential settlements structure can take. Well, likely like beyond that the structure will fail based on the particular like a K history. But anyways, like the differential settlements is a subject that like very likely the geotech need to work closely with the structural engineers, and it's quite complicated. Like that discuss, we cannot go too deep, but just give you some idea what may goes wrong. So if you get a chance to take the graduate level geotech design course, then like we will talk more on this issue. But at least at this point, my expectations for you is to know what is differential settlements and why that happens. And like when you see design values or design criteria, you will make sense to you, and you know what you're expecting. Okay, next, let's us talk about the secondary consolidations. So the big picture of this topic, again, we step back, we can learn this from a laboratory data. So here you get like a plot that is from a consolidation test. Remember from a 366, sorry, the 368 Geotech Lab. We spent a fair amount of time, 3 weeks of time, spending 2 weeks, two lectures that talk about this consolidation test. And here is a settlement curve. Remember, like in the lab, we have different loading, and each different stress level, we will get like a settlement curve. And this settlements curve tell us a lot about the um, soil deformations. And uh, throughout this lecture, we keep talk about this when we talk about the total settlements. So consolidation tests like settlement curve give you the total settlements. It come with three parts again. First, we have the initial settlement, the immediate settlements. Um, we have the primary consolidations, and also we have the secondary consolidations, which we try to focus on now. And actually, this graph, this settlement curve here will tell us the three different like sections by different slope. So first, like the immediate settlements give you the first slope, and then like the primary consolidations give you the second slope, and finally the secondary consolidation part gives you the final slope. And this chart or this graph, the x-axis is the time scale in log scale, and the y-axis is the deformations. So you read the dial gauge, you keep monitoring the amount of deformations, and each part of it gives you the slope. For these secondary consolidations is C sub alpha. Okay, so we have this like a three part of consolidations, and where's the source of the consolidation come from? So for the immediate settlements, it come from the expelling the air. So you have the void space, and like once you pace the loading, you get rid of the air, and so everything happens so quickly. So remember, like when you have soil, like a matrix, all this is the soil particles right there, and you do have the void. So the void here is kind of like in between the soil particles, and within those voids there could be air, especially like you're dealing with the soils that above the groundwater table is near the ground surface, so many of them are unsaturated. So you have the air void, and once you low on it, then like you compress quickly. So that gives you the immediate settlements. And the primary consolidations, we talk a lot about this in the 366, and where it come from is come from the expelling the air void, expelling the water from the cliff. So now those water trap in the void of the soil between the particles, the void space. Now you low on it, you squeeze out the water. So the reduce of volumes because of the reductions of the water or the volume of void, then it becomes your primary consolidations. And you need to be very careful. This whole thing is stress dependence. which means like if you like change the stress level, increase the stress level, the consolidations, the primary consolidations can be reinitiated, which means like what happened is like during the primary consolidations when you apply loading, and then like at a certain point there will be no more pore water from that given stress able to expel furthermore water, which means like once after you apply the loading, if you wait long enough to a point that there will be no more further water can be expelled out, and that point we call it as the end of primary. So here is your end of primary. We call it T sub P. And this end of primary means to a point that at the given stress, there's no more further pore water can escape. But it doesn't mean like all the pore water is gone. All the trapped pore waters, there's always like a tiny bit left there, no matter how high the stress you go, until to a point that like all the stress, all the soil particles, is got destroyed. Otherwise, there's always like a pore water get trapped. So I call this to be stress dependence. It's because this T sub B here is stress dependence, which means like the whole primary consolidations is stress dependence, which means like if you increase the stress level, there will be a furthermore pore water can push out because the increase of the loading. Or the other one, if you like take off the loading, then now you will have the rebound on the soil. You will be creating like a more void space, and the additions of the void space will kind of like create a suction force to attract the water back into the void. So you have the loading and unloading response, and we talk about that in our 360H lab too. But like anyway, so this is the end of primary, and a very important concept. This is stress dependence, which means like the behavior of the T sub P, the overall behavior of expelling water will be depends on the stress. Um, and to define the T sub P is defined by the intersections between the two slope, the primary slope and also the secondary slope. So the intersections point between like the primary sections and also the secondary sections, that would be your end of primary, the time of end of primary in the lab scale. So this is a lab data, and we can convert that back to the field data. And in 366 and 368, we talk about how to do that. So in order to calculate, for us to calculate the amount of deformations, which what we want, right? The amount of settlements from the secondary consolidations, the key parameters here is the slope of the C sub alpha, so which is this one. So this C sub alpha, we call it to be the coefficients of secondary consolidations. So if we can find C sub alpha and if we know the T sub P, and then we can calculate the deformations at the time of interest that we want. So the formula here on the left hand side is the deformations of secondary consolidations is equals to the C sub alpha times log the T divided by T sub P. So the T here is the time of interest. And T sub P, so the C sub alpha and the T sub P, those are measurements from the lab. So after you retrieve the soil samples, you ship it to the lab, and then you do a consolidation test. You get the settlement curve, then you can find out the C sub alpha and T sub P. And again, this is stress dependence. It depends on which stress level you're designing for. So now you know the C sub alpha and T sub P, and at the time that you want to investigate, then you can find out the because you know this one from the lab, you know this one, and this is from the design time that you want you design for. So you know those three parameters, then you can find out the deformations. And for examples, like from the lab, coming back from the lab, you know the end of primary at is like a 40 years. So you know T sub P is equal 40 years, and or like is something that, or like the design is more likely is you find out the um, this well so from the lab measurements, you know the C sub alpha, and then like you back calculate that, you know that you corresponding to T sub P, the end of uh, primary consolidation is like a 40 years, and you want to investigate the um, consolidations up to 50 years. So your T now is 50 years, the T sub P is 40 years, and then you know the C sub alpha, then you can calculate the deformations. So we do an example afterward, hopefully like give you some real data, and then you will be make more sense to you. So some more points about this secondary consolidations. First, this is we're talking about the additional time dependence compressions after the primary consolidations. So this is secondary consolidations, and we're looking at a time that like there's no more dissipations of excess pore pressure, which means there's no more squeezings out of water. And this is like also relatively small amount of volume change compared um, to the primary consolidations, as you can tell like from the slope of the curve. So the slope for the primary consolidations will be much the weight or the slope there much greater than the one that form the secondary consolidations, which also physically makes sense because for the soils, is the deformations or like is easier to push out the water rather than try to reorganize the particles. So we talk about the source for the primary, and then the source for immediate settlements, and the source for the secondary consolidations is because of the creep. Also requires usually the terms called creeping, or the particle orientations. So that's just the source of secondary consolidations. Uh, because like now, like no more water that coming out, but the deformations is come from the reorganizations of the particles. Sometimes you even like deal with like because it has been there for the stress has been there for so long, so now it start to deform, have a very slow rate of the constant deform of the soil particles. So that gives you the secondary consolidations, and also maybe some organic decompositions. So if there's any chemical reactions uh, involved in the soil and water and the pore fluid, then we'll give you deformations that also belongs to the secondary consolidations. And the C sub alpha is independent of the time, um, is independent of the thickness of the soil layers, and also very important, the ratios of C sub alpha and the C sub C, the compression index. So you can get the compression index from the ELOP curve. We talk about that in 368. And the compression index is a very important parameters for you to do settlement analysis. But the ratios between the C sub alpha that you obtain from the lab from a settlement curve divided by the C sub C you obtain from the ELOP curve is a constant. And this aspect will be useful for us to estimate the C sub alpha, which we will talk about next. Okay, so we talked about the terms of C sub alpha derived by C sub C, the ratios being constant, and it can be used by like by some like typical numbers. For examples, this table here give you some typical numbers for the ratios here. So for if you have like summary classic material like San Francisco Bay mud, you have the number. You have other like soils um, like the problematic ones like the peat. Then you have the numbers like when you have organic matter, the secondary consolidations is something you really look at. But anyways, like those those like ready to go number can be handy when you don't have a consolidation test to get the C sub alpha. Sometimes the lab testing could be too expensive to be afforded for a small scale project, or like if you want to uh, have some ballpark number to play with at the beginning for a preliminary design, those number can be used too. So if you look at our formulations, we don't know our C sub alpha if we don't have a consolidation test. But if we play around with the math, so by the way, this is the equations for calculating settlements, right? So we talk about this in 366. Actually, like um, so that is a deformation part, and then times um, the initial wire, related to the wire, initial wire ratios, and so this is the initial wire ratios, and this is the pretty much is the thickness of the solid layers you look at. Then you get this total settlements for your site. So pretty much like we can convert the lab scale. So this is the lab scale calculations. So this is those orders like from the lab parameters, and then like now we apply that into in the field scenario. Then so those are field parameters. So this is the thickness. Um, so now even though you don't know your C sub alpha, but if you play with the math here, you divide it by the C sub C and times C sub C. So C sub C is a parameters that like are more common. So this is a constant, and this is more typical. Then you could estimate the settlements. So when we will consider the effect of or like when we need to take into account on the secondary consolidations. Well, first of all, like if the ratios of the secondary derived by the primary is the settlement is greater than one, so which means like you wait long enough that the settlements for the secondary consolidations is more even more significant than those from the primary consolidations. So when if the time is long enough, if you design a structure that you will be last for like many years, in terms of hundred or like even like a couple hundred years, then for sure you need to look at secondary consolidations. And for the field, if the end of primary is relatively short, for the soil, then you also need to like seriously investigate the secondary consolidations settlements, and also if the final stress that you get is in the compression range. Remember, like in 366 we talk about this. So this is the maximum pass pressure, uh, and you'll have your initial stress like could be anywhere, right? But and then if you and this region here. So this is the compassions. This is the virgin's compassion part. So this is the compassions. So the those E log B curve is this is the void ratios, and this is the vertical stress, and if this is C sub C. So if your final stress is within this like a compression range, then you will better like also look at the secondary consolidations. And when you have very high PI, then and also highly organic soils, you also need to particularly look at the secondary consolidations uh, settlements. So remember, like our kind of like typical data or experimental data tell us the secondary consolidations, like deformations, can be insignificant compared with primary consolidations. So for typical soils or like for a small scale project, for building that doesn't have a very long design span, you maybe can get away from not looking into the secondary consolidation settlements. But like for particular scenario, you better like look at the that topic when you have those considerations. So this always need to be at back of your mind. Okay, and when the secondary consolidation start, so we define the from the previous like a data or previous like slides, we define the secondary consolidation start only like the primary consolidations has finished. And actually, from the research side or from the clay science like perspective, this is not right. And there's experimental data so that during like the primary consolidations, there's proof that actually the secondary consolidations has started with the primary. So it's very complicated. It's a little bit more going into the clay science on how the soil skeleton response, right? Remember, like secondary consolidations means the reorganizations of the soil particles. The primary consolidations means expelling the pore water. So it's not that's like a not a clear like difference between when to start, when to stop, and it's not like after expelling all the water they can expel, and then you magically you will start the particles start to reorganize itself, or how to start when to start to deform the soil particles. More very likely, the two happen together. But if you want to have a very accurate like a details like number from those two, that would be almost impossible. His small become like a scientific problem rather than engineering problems. So it's not something like easy you can easily like distinguish between the two and then find the exact number. So so it's more become like a research topic than an engineering practice. So engineering practice, we still within the ballpark, we still can do our analysis like as the way that like end of primary and then like you start the secondary. But as an engineers, you better understand what's actually going on too and what kind of assumptions we are making. So in fact, what is the true soil behavior behind is when both the primary and the secondary consolidations they happen together. But in our engineering interests, we separate down. So if you want to learn more, this pretty much like become a research project, or like could be a PhD topics that like you can spend a couple of years in grad school to investigate. And for engineering PhD students and whatever you find out, you need to make it practical. So that's a little bit difference between the engineering research versus the scientific research. So anyway, so this is more typical parameters to use for the C sub C. So if you want some numbers for design for C sub C, because the C sub C can be powerful when you calculate the settlements involving the secondary consolidations. So this is secondary uh, consolidations settlements calculations. And if you have typical soils that you can compare with, then those are the numbers. And if you have a lack of experimental data, because again, like those consolidation tests can be very expensive. Um, And if you want some correlations, the C sub C related to the initial void ratios, E naught, or the W here, the water content, then those are some correlations by some researcher. And also, like in the past research, based on uh, the available data, so from different soils that which are all named here from number 1 to number 11. So the those are kind of like a typical soils, and um, people find relations, correlations between the C sub alpha and the water content. So, but you can see the scatter there, so it's quite uncertain. But if you don't have again, if you don't have a lab test, those are empirical correlations, could be useful. But you need to use that with a lot of like care. Be very careful on those correlations. Sometimes you work, sometimes it doesn't work, and you may not have the experimental data to prove it. So be very careful with those empirical correlations.